Okay, so yesterday we finished here. Here is a single smooth tip. Okay, we finished here. So it allows rotation. It allows rotation this way. So therefore, it cannot provide a rotation resistance for x-axis, but it can prevent rotation for y and z axis, and also it's pin connection, so it can have 3 directions of reaction. Okay, then next one is a single hinge. So from this figure, this kind of design, it can rotate this way, so it cannot provide a resistance for this direction of rotation. The other unknown information, other reaction can be provided. Okay, then final one is fixed support. Fixed support, so very common, can be seen everywhere. So 6 reaction all can be provided. Okay, that's a fixed support. Okay, so from these 2 slides, here and here, we know what kind of support can provide what kind of reaction. So based on those information, we can go to 3-dimensional problem, okay, and solve their reaction. Okay, here I'll show you some figure. This one is ball and socket support, look like this. Okay, then this one is a journal bearing. Journal bearing, which is this one. Okay, and this one is thrust bearing. Okay, so it's this one. Okay, then this one is pin support, so it's this one. Okay, then we go to a 3D problem. Considering the 2 rod and plate along with their associated free body diagram, okay, shown here. The XYZ axis are established on the diagram, and the unknown reaction component are indicated in the positive sense, and the weight is neglected. Okay, anyway, they are 3 different cases. So look at first one. By observation, because in order to draw a free body diagram, we need to observe the case. So this kind of support provide Z and Y axis reaction. Okay, similarly, for point B, also provide Z direction and X direction reaction. Okay, point C is Y direction and X direction. Okay, then 500 and this moment is original layer. So that's a free body diagram for this case. Okay, then bottom left. So this is pin supported. So look like this. Okay, so for this case, it can have 5 reaction. Because for Y axis bending moment, there is no reaction. So we don't need to consider it. Okay, and that's the original force and moment here. And its cable connection, cable only provide tensile force. Okay, so tension here. So free body diagram for this case, button F look like this. Okay, then for point bottom right, point A reaction. Point A reaction, yes, similar to this case. Okay, so it's X and Z axis reaction. Okay, then that's the external force, original layer. Okay, then that's a roller support, so only normal force. Okay, then for this single hinge, it can provide three direction of force, and theoretically, it can also provide rotation this way and also this way. So please draw. They also provide a rotation this way and this way. Okay. Okay. So using equivalent equation, we can work out unknown reaction. So similar consideration to two-dimensional problem. So we use equilibrium equation, we can solve our unknown. Okay, unknown is like loss reaction support. So by using equilibrium equation, three-dimensional problem, okay, of course, we still use summation F equal to 0 and summation of bending moment equal to 0. So we still use these two approach to work out our unknown parameter. Okay. So actually, for summation force, we still can divide this part into three components. So X, Y, Z, three directions. Okay, the same as bending moment, we can work out three directions of bending moment. And by considering this, okay, they don't have influence on different axes. So actually, first equation we can obtain. So summation X direction of force should be equal to 0. And sigma Fy equal to 0, okay? Summation Fz equal to 0. So here give us three equilibrium equation. Okay, the same concept. For bending moment, we also have three equilibrium equation. So totally, theoretically, for general equation, we can have 6 unknown. Okay, not 6 unknown. We can have 6 equilibrium equation, and therefore we can solve maximum 6 unknown parameter. Okay, 6 equations solve 6 unknown parameter. Okay, for some case, if our equilibrium equation, the number is less than unknown parameter, Okay, 6 equilibrium equations solve 6 unknown, but some case it's possible we have unknown parameter more than equilibrium equation. Okay, I just give you some idea. For example, for two-dimensional problem, we will solve fx equal to 0 and fy equal to 0 and bending moment f equal to 0. Okay, wait, for 2D case, we have 3 equilibrium equation. Okay, so for general problem, simple problem, here is hinge, here is roller. So hinge or peak connection, we can provide reaction X and reaction Y. Okay, here we call as a point A. Okay, RYA and RXA. So here is point B, roller, only normal. Okay, so normal is RYB. Okay, so 3 equilibrium equation solve 3 unknown. Okay, but if here we change it become hinge, so hinge will give us R Y not R Y RX B and RYB. So it becomes we have 4 unknown, but we still have 3 equilibrium equation. So we don't have enough condition to work out the answer. Okay, so this kind of situation we call as indeterminate structure. Indeterminate structure. Okay? But you have to keep in mind, indeterminate structure theoretically is safer because you give one more constraint. Can you understand? Can you imagine? Because you give more constraint, that means safer. So theoretically, more we provide more reaction, more constraint. Okay, it will be safer. Okay, and in this subject, we are not discussing this part. How to anyway, how to solve it is not the main concept, main topic in this subject. So theoretically, for indeterminate structure, they will be taught in structural analysis. Okay, not this subject. Because for solving indeterminate structure, of course, not just one approach, several approaches, but theoretically, you should consider material behavior. Okay, because material behavior can help you to solve indeterminate structure. But we are not discussing here. So you just know if equilibrium equation is less than unknown, less than reaction, we call as the indeterminate structure. And most of I'm not sure about mechanical equipment, but most of civil building, I'm talking about building, most of civil building, they are indeterminate structure. Okay? Because like feet, here we cannot see it, but like feet, 2 parts, we fix it. So if fixed, so that means for 2D case, that means it can have vertical and horizontal reaction and also have bending moment. Okay? And this part is also fixed. So also 3 reactions. So for civil problems, most of them are fixed 2 sides. Because for civil construction, simplifying the support is not meaningful. in terms of cost, they are similar. So if similar, why not? We don't make it stronger. Okay, more constraint, that means stronger, safer. Okay. But in other area, I'm not pretty much understand what's their consideration. But civil, most of them for building. Okay, I'm not talking about other. For building, most of them are fixed, not fixed, determined structure. Okay. Okay, here, just show you for 2D. This is a 2D case, and 2D case we have 3 equilibrium equations, but we have 5 unknown. 5 unknown for this case. So what's the 5 unknown? We have reaction for point B and point C, and point A is fixed. Fixed can have 3 reactions, so total 5. Total 5. Okay. Okay, for 3D problem, this case, this part, point B, is fixed. So fixed can have 6 unknown. Okay, for fixed. And here is, I can't remember the name. Okay, it's a journal period. So, not journal period. Should be only 2. Okay, still journal period, but there is no rotation. Okay, so for point A is only y-axis and z-axis reaction. Okay. So actually we have A unknown, but for 3D problem we have 6 equilibrium equations, so we cannot solve it. Okay, we cannot solve it. So it's also indeterminate problem. Okay, then next part we talk about improper constraint. That means this kind of support is not proper design. Okay? And what's not proper design? For 2D problem, theoretically, one side is hinge, the other side is roller. Okay? So it can provide reaction look like this. But if we change point B reaction here, so that means point B provide force here. Okay? But when you provide force here, we have an external loading here. Okay, so that means the overall structure can rotate. Can you imagine? The overall structure can rotate. So that means it can rotate, it's not stable. So that's an improper design. Okay, how to verify it? Because if we take a bending moment at point A, these 2 forces pass through point A, so we don't need to work out the bending moment. And this force also pass through point A. And that means external loading will give a bending moment, but we don't have reaction to prevent the rotation. So it's not a stable condition. Okay, so we call as improper design. Okay, then for this case, A, B, they are ball and socket support. So ball and socket support only provide 3 direction of force. But we have external loading here, applying at this point. So that means the overall structure still can rotate. Okay, rotate this way. Rotate this way. Okay, and it's also improper design. It's not a stable situation. Okay, then next one. A and B, both of them are roller support. So roller support only provide vertical reaction. But here, external loading is inclined. So it can have horizontal and vertical component. Okay? Vertical component we have reaction, but we don't have constraint to support horizontal force. So still not stable. Okay? And then next one, they are you can consider they are cable. Okay? Cable only tensile force. So all of them upward. But we have an external loading this way. So that means it will shaking later. Okay? So it's not stable situation. So they all call us improper design. But of course, for some case, particularly close to Christmas, okay, so that's kind of decoration. Okay, but anyway, in Taiwan, we don't use this decoration too much, even for structure. Outside decoration, the reason is we have earthquake. Okay, so this kind of shaking, maybe they will drop somewhere. Okay, so like, do you see the news from there is a construction field, a leaf crane, something dropped. So the condition is like this. Okay, during earthquake, there is something dropped from leaf crane. Also in Dan district, I don't know which road, but during earthquake, so something dropped from leaf crane. So the condition is like this. Okay, because you only have tension above, but shaking you cannot prevent it. So that's the reason Taiwan we don't have this. Leaf crane use this is temporary. Okay, so permanent structure in Taiwan we don't use this way. Okay then. Partially constrained. Okay. Fewer reactive force than equation of equilibrium. So actually. You can imagine these two, this section and this section. Do you remember what's the definition of two force member? Do you remember two force member? We have two nodes, 2 points. Okay, loading acting on it. No, there is no additional loading. No additional loading. So for two force member, the force, okay, that's the element. The force must be along this line, and then their magnitude is the same and opposite direction. So That's called two false member. So actually, this element and this element is two false member because they only have point here, point here. Okay? So two false member already mentioned, their force must be along this way. Okay? So they must be along this way. So that means there is no vertical loading. Do you agree with that? Must be along this. Okay, so from these two, we know force must be there. But we cannot balance it. Okay, so it's also improper design. Okay? Clear? It's two force member. Okay, so we go to example. The homogeneous plate here has a mass of 100 kilogram and is subject to force and couple moment along its edge. Okay, force here, couple moment here, and if it is supported in the horizontal plane, by a roller at A, ball and socket, B, and core, C, so determine component of reaction at this support. So ball, that means only normal. Okay, ball and socket, 3 direction of force. Core, only tensile force. Okay, so that's a free body diagram. Look like we have self-weight, external loading, couple moment, and 1, 2, 3, 4, 5. 5 reactions. Okay, then we can apply equilibrium equation to work out the condition. So by observation, so vertical force, vertical. Okay? And these two horizontal force, we don't have other loading to balance it, to cancel it. So this Bx and By must be 0. Okay? Clear? From our observation, we know no other force can balance Bx and By, so they must be 0. Okay, and that means for Z direction, summation all of them should be equal to 0. But AZ, BZ, and TC, all of them are unknown. Okay, then we can consider other equilibrium equation. So to solve, particularly to solve bending moment, observation is very important because we want to choose a point can reduce our calculation procedure. So we know A, B, and T, C, they are unknown. So they are two-way. If we take bending moment for Y prime, because this AZ and BZ force all pass through the moment we are taking. So that means we can reduce two unknown. So we only work out TC. Okay, the other way is we take a moment for X prime. So we can reduce unknown this part and this part. We can work out AX. So from my observation, I prefer starting from X prime and Y prime, these two axes, to work out a solution because it can help us to reduce unknown. Okay, but from their procedure, they work out bending moment for x-axis. So they are taking bending moment for this. And theoretically counterclockwise is positive. So TC give counterclockwise bending moment. Level arm is 1 meter. Oh, 2 meter here. So level arm is 2 meter. So which is positive. Okay, self-weight give clockwise moment. Okay, along x-axis is clockwise moment. So it's negative. And level arm is 1 because that's a uniform plane. So center point is self-weight applying location. Okay, then BC. BC is here. Level arm is 2 and also counterclockwise. So we work out the equilibrium equation here. Okay, then the second equilibrium equation for y-axis. So 300 counterclockwise moment, level arm is 1.5. And also self-weight, level arm is also 1.5. Okay, also counterclockwise moment. So both of them are positive. Okay, BC is negative, clockwise moment negative, and level arm is 3. And the same, AZ level arm is 3. Okay, and clockwise moment. So we have two equilibrium equation and sorry, I forgot to mention this. So for y-axis, bending moment, couple moment this way is negative, so minus 200 here. Okay, then right now we have 3 equilibrium equations, so we can solve 3 unknown. Okay, 3 equilibrium equations solve 3 unknown. Okay, then the second approach is what I mentioned previously. We take a bending moment for x plot and y plot, so we can reduce unknown parameter. You see, if we take a bending moment for x plot here, so TC and BC, we don't need to consider it. Only AZ is unknown parameter. Okay, so we can work out AZ from this equilibrium equation. X plot is here. So 300 and 981, both of them provide counterclockwise moment, but with different level up. 1 meter here. 2 meter here. Okay, then using this we can work out AZ. So the same for Y plot. For Y plot, we can work out TC, and then TC. So we have bending moment contribution from this and these two. Okay, for Y plot, the same 200 is negative, and TC is counterclockwise. Level arm is 3, and 300 they are clockwise moment, so negative. Level arm is 1.5, and 981 also negative contribution. So we can work out TC. So we know AZ, we know TC. We pull them back to first equilibrium equation. Okay, we know TC, we know AZ, so we can work out BZ. Okay, clear? Okay. Next example, determine the component of reaction that the ball and socket joint are A, the smooth journal bearing are B, okay, and the roller support are C, exert on the rod assembly here. Okay, ball and socket, 3 different directional force, and journal bearing, 2 horizontal x-axis and vertical z-axis reaction. And here is roller support, so only normal direction. So normal direction is z direction. Okay, then external loading is 900 here. Okay, free body diagram look like this. Our requirement is we want to know the reaction for all of them. So first stage, from our observation, we can see there is no other y-axis or y direction force except AY. Okay, so no other y direction force, only AY. So AY must be 0. Okay, AY must be 0. So when AY 0, that means we only have phi unknown. So phi unknown, if I solve it, I will take a moment for y-axis because I can directly solve what's the FC value from bending moment. Okay, so taking a moment for y-axis here. And 900 give negative bending moment. FC give positive bending moment. So that's a level up. We can work out FC is 600. Okay, then we know FC, and we can take a moment for x-axis, which is here. So we don't need to consider AX and AZ. And also for x-axis, we don't need to work out BX as well, because BX bending moment is for z-axis, but our consideration is x-axis. So only for B point, only contribution comes from BZ. Okay, so from equilibrium equation, BZ for x-axis give positive contribution, level on is 0.4 plus 0.4, 0.8. Okay, then FC is 600 from here. So it's upward. So it's also counterclockwise moment. Level on is 1.2. Okay, then 900 level on is 0.4. So clockwise moment. And then equilibrium equation gives us BZ is negative 450. So negative means the force direction is opposite to what we assume. So that means BZ, the force is downward. Okay, so BZ is downward. So we know BZ is downward, and FC is upward, and 900 is downward. So equilibrium equation can help us to work out AZ. Okay? Then, if we take a moment for z axis, so actually we can work for z axis. Okay, and 900 FC and also BC, they do not provide bending moment. Okay, for z axis. So that means Bx must be 0. Bx must be 0. Okay? So from if Bx 0, that means Ax also 0. So by considering all equilibrium equation, we can solve those unknown reaction. Okay, clear? So, next example, the boom is used to support 40 kg from flower pot. Determine the tension developed in AB here and AC. Okay, so we have tension here, and here is ball and socket support. Okay, so its free body diagram look like this. Okay, tension, ball and socket support, flower pot. Remember, unit transfer here. Okay, then they use vector to solve the problem. Okay, AB, do you still remember how do we work out position vector? From A to B, so we use coordinate A minus B. So that's a position vector divided by its length, become unit vector. So unit vector times force. Okay, we don't know. We just assume it like FAB. So that's the force AB presented by Cartesian vector. So similar approach for FAC, position vector, you become unit vector and then present the result like this. Okay, here is FAB, here is FAC, and here this flower pot self-weight, we can also present it using Cartesian vector. Okay, so they use the equilibrium equation for point O. Point O is here. So to work out moment for point O, use cross product. So cross product. Remember, we can have any position vector cross force vector, okay? But all force, they all intersect here. That's a concurrent situation, okay? They all touch the same point. So we just use one position vector cross these three forces together, and this position vector is RA. Okay? So use cross product and they should be equal to 0. So RA, this position vector is 3J follow Y axis. Okay, and as I mentioned, flower part weight, that's a unit transfer. We also can present it using Cartesian vector. So it's here. So here is the for this point, okay, all force plus together. Okay. Position vector cross force vector should be equal to 0 for the moment calculation. So that means this part can be simplified as this. Okay? IJK. Okay, like J plus I give negative K because IJK. J cross I give negative K. Okay, so this part is negative K. Still remember how to work out cross product. One say yes, one say no. Remember I, J, K. So counterclockwise is positive. So first part, J, I give, is positive. So Ji, that's opposite direction, so negative. Okay? Ji give us negative K. So Ji give us negative K. K is here. Okay? Okay, Jj is 0. JK give us I positive. Okay? So JK give us I positive. So FAB, so positive. This way. Okay, similar. And to calculate, this part can be simplified like this. So for this component should be equal to 0. This component also equal to 0. So we can have this and this. And two equilibrium equations to work out two unknown. Okay, that's it. Okay, we take 10 minutes break. Okay, so we keep on next example. Rod AB, this one, is subject to a 200 Newton force. 200 Newton force right here. So determine the reaction at the ball and socket joint A here, and the tension in the cable BD. BD is here. Okay, and BE here. Because it's cable, so only tensile force. And the corner RC is fixed to the rod. So it mentions the corner here is fixed. That means it cannot move. Okay, and apply force 200 at point C here. And for point A is ball and socket. So ball and socket 3 direction force. Okay, and BD and BE tension. So tension. So free body diagram look like this. Okay, the requirement is determine the reaction at ball and socket here and tension here. Okay, anyway, for this question we have 5 unknown. Because ball and socket have 3 and tension is 2. So total 5 unknown. So 5 unknown, that means at least theoretically we should have 5 equivalent equations. Okay, then for force A, okay, here reaction A, so we can use this way to represent the condition. And BE, we can represent using this. BD is this one, and force applied 200 is downward, so negative 200 kN. Okay, so we know, now we use those information to represent all of that. So theoretically, because it's achieve equilibrium condition, so plus them together, they should be equal to 0. So we can present it using this way. Okay? And then that means this part for x direction equal to 0, y direction equal to 0, and z direction equal to 0. So that means AZ. Okay, we already know it. Okay, then the second approach, the second procedure is we take a moment for point A. So use cross product. So first they use first part RC cross F. F is this 200. Okay, and then RB cross TE plus TD. Okay, RC position vector presented here. Force vector from here, negative 200 kN. And RB position vector is here. So RB is double RC. Okay, it's double. Because RC is halfway. So that's the reason RB is double. Okay, then TE, TD here. So for cross product calculation, so this part can be simplified as this. Okay, so that's an MX component, MY component, MZ component should be equal to 0. So first part, MS component, we can work out TD. Second part, MY component, we can work out TE. Okay, so TD, TE, we already know it, TD, TE. And from previous part, we know AZ. Okay, TD, TE, AZ, we know first. Okay, then from previous part, we know TE, TD, we can work out AS and AY. So AS and AY is, are also obtained. Okay, clear? Okay, then the band rod in this figure is supported by not by at A by a journal bearing here, at D by a ball and socket joint, and B by cable BC. Using only one equilibrium equation obtain a direct solution for the tension in cable BC. Cable BC. Okay, the bearing RA is capable of exerting force component. Okay, anyway, first part is we try to work out free body diagram. So, journal bearing, so we can have vertical and horizontal force as a reaction. Ball and socket, 3 directional force here. Okay, then cable here. But we want to use one equilibrium equation to solve it. Okay, that's a requirement. So theoretically is we try to use this equation which can reduce unknown parameter as many as possible. Okay, so I guess the beta wave is we take a moment for this axis. Because we take a moment for this axis, all reaction from A and D, point A and point D, we don't need to consider it. Okay? We take a moment for AD axis. Okay, so it's probably the reason, first of all, we work out the unit vector. dA, okay, position vector from D to A, okay? So unit vector. Okay, so we take a moment along dA. So achieve equilibrium. Okay, so this part actually we can have UD vector. Okay, because we take a moment for this part, so we need the position vector cross product. So from the procedure, they use RB cross TB plus RE cross RE cross W. W is the loading here. Remember unit transfer. Okay, then unit vector dot this cross product, okay, should be equal to 0 because for dot product, that's only magnitude. So the magnitude should be equal to 0. Okay, so that component RB is here, and TB we represent you in this way, and RE is halfway to RB, so RE is this value, and that's the weight for this cylinder. Okay, then this part J, I, J, K. So J, K give us positive I, but here is negative. J, K give positive I. Okay, then so positive I is here, but negative here, so put negative here. And JK also positive I, but negative become positive. and positive I, so totally is positive. Okay, so we can work out here. And then dot product, make it as a 0. So TB is this value. Okay, then we can directly work out the TB using Cartesian vector. And the bottom is second approach. They also take a moment for this axis, okay, AD or DA axis. Okay, then they directly work out the distance, okay, and taking a moment, bending moment. So because the vertical distance, this distance is halfway to this, okay, triangle. You do triangle halfway. So we know weight is 981. So TB must be half. Okay, because level up is double. Okay, so we still can work out the value is 490.5 Newton. Okay, and then this one, the uniform rod AB has a mass of 440 kilogram max. Uniform rod AB, okay, here. Determine the force in the cable when the rod is in the position sharp. Okay, there is a smooth collar at A. So theoretically, here is cable. So tensile force. Okay, and then for point B is normal reaction here. Okay, the uniform rod. Okay, then which is uniform. Okay, so theoretically, if uniform, that means the loading, the weight is center. Okay, clear? Center. So we have the loading come from here, loading from cable, and also normal reaction from here. And here, although it's a smooth collar here, and it also have a reaction. Okay, we don't know take a moment for okay, it's smooth rod. Smooth. Okay, smooth that means it can move that way. Okay, it can move that way, that means there is no vertical reaction. And then we have a weight here. And vertical support must be from here. Do you agree with that? Okay, we have self-weight. So it should be, vertical loading should be supported by here. Okay? Okay, then we can take a moment for this point because we know moment contribution from this reaction and also moment contribution from the self-weight. So we can work out moment from table. And not moment from, we can work out the force. And then, because we know what's the level up here. Okay? So that's the overall procedure.
So if the support in A doesn't have vertical direction, then the route just slips out.
But this slip down. It cannot. The reason is this. You imagine this golden one is like a ring. Okay, it's like a ring. So this bar, okay. This bar will support it. Don't slip because it's the tension. Fix it. So it cannot move. Okay, this part, it cannot move. And this will provide, here, will provide vertical and horizontal force. Okay, so it will link to here. However, this part is smooth. Theoretically, it can move up and down, but supported by here. Can you imagine? You have to think that's a ring. Okay, outside maybe they connected by this, but inside is smooth.
Inside is smooth, so it can just slip down.
Yes, but supported by here. Because that's a connected structure. So reaction is come from here, not from here. Can you imagine?
If your hand like this, support this, and then if nothing hold this, you can slip down. If no vertical direction.
But outside, they still have a support come from this part, not inside. Okay, you have to imagine. We don't calculate the bar. We calculate is like my hand. Okay, you use your hand. So your hand is the golden part. Okay, so your hand will not go down is due to we have this to support it, not due to this, not due to the bar. Okay, it's due to we have you consider my elbow. Okay, is this point. Can you imagine?
So the rock and the golden part is already linked into one.
Already linked what?
So the rod cannot slip away from that folding part because of the head.
Yeah, because head supported by here. Okay. Okay, then this one determine the distance d. Distance d for placement of the log p. Log p. Distance d and log p for equivalent of the smooth part in the position theta. So actually, this condition, anyway, they are all smooth. So a bar look like this, and theta here. So theoretically, we have a reaction vertical. Okay, normal here. Okay, then this distance is A. Okay, here we also have reaction. We don't know it. And here is the loading P. Okay, what's the requirement? Calculate the weight of bar, so we don't need to consider the weight of bar. Okay, then here is this is length d. Okay, determine d for placement of the log p or equivalent of smooth bar in the position theta. So last thing, we want to work out what d is. Very young. Okay, if we take a moment for this point. Okay. So but we have one more unknown information. So if this is V, so that means we have term D. Okay, theoretically, NB
这是明天即将到来的 NBA 比赛，其实相比
I didn't call NBA. Okay, NB we have NB Y. Okay, here is NB X. Okay, you know, vertical and horizontal component NBY and NBX. So, NBY and NBX here is also theta. Right? Here is also theta. So I'm thinking NBX should be equal to this or no. Still have one more reaction. Is NA. The position theta. Position theta shown on left weight. So we have these two. We want to replace it. Okay, so this okay, I have to think about this question. I haven't studied for a long time. Let me think. This. Because anyway, we use equilibrium equation, and but taking a moment from which point. Distance D for basement of log P. for equilibrium of smooth part in the position theta. Position theta. Okay, anyway, I solve this question next time. So we go to next one. Okay, then this equation is a boy stand out on the end of the diving board. Diving, okay, which is supported by two spring, A, B, and each having a stiffness 15 kilonewton per meter. Okay, remember unit transfer because here is 40 kilogram. In the position shown, the ball is horizontal. Okay, here, right now it's horizontal. So, if the boy mass is 40 kilogram, determine the angle of tilt which the ball make the horizontal after he jump. Okay, ignore the weight come from the ball. Okay, anyway, my drawing is not good, so I use this to represent the boy. Okay, and A here 1 meter, B here, so here is 1 meter. Okay, here is 3 meter. So before he jump is horizontal. So after he jump, of course, it's not horizontal. So theoretically, that's a point A and point B. Okay, so we can take bending moment A equal to 0. Okay, so that means 40 counter clockwise. So for 40 need unit transfer. So 40 times by 9.81. Okay, so that's the loading. I don't work out here, but anyway, unit transfer. You have loading here. Level on is 4. Okay, and that means RB is this way. Okay, come from stiffness. That's the RB. Come from spring. RB is this way. So this is this way and that is this way. We can work out RB. We take a moment here, so we can work out RB. Okay, and total vertical force should achieve equilibrium. So that's the second part. X, Y, okay. So we know RB, we know this. We can work out this. So based on this loading condition, I saw RA is force is this direction. Okay. So to make it flat, make it horizontal, that's a loading condition. Okay. When it's horizontal, that's a loading condition. Okay. That means this person stand here, so it provides a reaction this way. And when he jump, that's the opposite. Okay? Because we compress it, so it provides a reaction here. So when he jump, so this compression is not there anymore. Okay? So it will, you can see it's bent. Okay? So the same thing. Previously, here is expansion, but after he jump, it become compression here. So using this way, you know the loading here, you know the stiffness, and then you can work out the displacement for it. And you have displacement, you have distance, you can work out the angle. Okay? So that's the overall concept. Okay, next one, the beam is subject to the two concentrated load. So here. And assuming that the foundation exert a linear varying load. So here. So distribution on each partner determine the load intensity W1 and W2 for equilibrium in terms of parameter shown here. Concentrated load. Okay, anyway, still follow equilibrium equation being here. W1, W2. P and 2P. Okay, and this term, they are all the same. 1/3 L. Okay, L is here. So theoretically, okay, this shape we can separate, easier for calculation. So it becomes a rectangle and a triangle. Okay, so for triangle, center of gravity is middle. Okay, rectangle is middle. Triangle is 1/3 here. Okay, 1/3 here. So we can take. I saw the easier way is any other color? Triangle 1/3 here. Okay, so the same as 1/3 here. And rectangle is middle. Okay? So we can take moment at this point because we can cancel these two. Okay? And then this one, this resultant is W1 times L. Okay? This resultant is W1 times L because of this area. Clear? So we take a moment at this point. So that means P times by 1/3 L should be the same as W1 L, okay, times by 1/6 L, okay. So you can work out what we need. Determine. Okay, we can work out W1. Clear? And the same. You know vertical loading, so you can work out W2 as well. Okay, so this question we have a solution procedure here. So its consideration the same as what I did. We take many moments at this point. Okay? And we have this. This is what I mentioned here. Okay? So the same, and then finally use vertical loading, achieve equilibrium. Okay, that's overall consideration for this equation. Okay, I want to discuss with you anyway, the TA, they are still marking your midterm exam. Okay, if possible, I will return next week, but if they haven't finished following week, okay? But I want to make sure the next final exam. And do you remember when is last final exam? Second of April. No, last midterm exam. 2nd of April. Okay.
No sé si fue el 2 no sé.
We make okay, we make next midterm is 30. Do you prefer 30 or do you prefer 30 of April or 7 of May? 7 of May? Huh? If 7 of May, please raise your hand. Okay, and if 30, raise your hand. Okay. 30 of April, 30 of April is the amount is smaller. Next midterm.
Because it's gonna be more project.
But 30 of April, the people raise hand is less. So theoretically 7 of April. Okay. 7 of May. And I want to check with you the final exam duration is first week of June, am I right? First week of June. Yes, it is. Okay. So that means 7 of May. You still have 4 weeks to reach the final exam. Okay? Okay, so 7 of May. Why you are smiling? That means this subject is too simple for you.
No.
Okay, so any question for today's content? Okay, if not, see you next week.